So yesterday we did stretches and shrinks horizontally for sine and cosine curves, A's and B's, right? A was an amplitude. How high above or below an axis line are you? B told us about how the period of the graph is going to be affected. So what we're going to do today is add to this list the C and the D. So here's our generic equations: y equals sine A sine B, x plus or minus C plus or minus D, and then the same thing can happen with a cosine. So if I were to change these C and D's into H's and K's, would you know what they're supposed to do? What would they do? What about those? What am I doing to those points? Moving them, exactly. So I heard somebody said vertex. That would be true if we had a parabola or an absolute value. But yeah, this is our new. These C and D values are shifting. So C is called a phase shift. And it just tells me how I move my graph left or right. And then the K is actually a way that we find our center axis, called our horizontal axis. And it's how we find our axis line, or thinking about moving my graph up and down. So that's what we're going to do. Same things as it had done to our other functions where H's and K's were involved. The reason we're doing A, B, C's, and D's is we started with A's and B's. We're going to just continue with the C and D trend there. So H and K, in the book they use H and K. We're going to use the C and D concept. And also this D. This D could be rewritten on the left-hand side with Y. And if that were the case, if I have Y minus D, for example, that would mean I go up D units. If it was Y plus D on the left-hand side, I would go down D units. So it's just like the behavior you have when you are in the C world. Real quick, get down here to the C's. When it's an X minus a C, that means my graph is shifting to the right C units. And when it's an X plus a C, we're shifting to the left C units. We're going to put the D on the other side of the Y, and that is when you just see, take what you see. So if you see a plus 5 as a D value, that means you move up. If it's a negative 5, you move down. So we have these two equations, amplitude, A, we did that one yesterday. Period, we did that one yesterday. So those are not new. C and D are the only new things here. Phase shifts and horizontal axis. And we introduced this third equation for the D. What does it look like? Look familiar? It looks a lot like the amplitude. The only difference is I'm adding the max and the min. So I'm thinking of an average. Exactly. Looking at the average for those two. Okay. So periodic. Remember, we're talking about modeling, and we have a couple scenarios. Like, I know some of you guys in physics right now, you're actually talking about this stuff right now in physics. You guys are doing light and sound. Is that right? Anyone in here in physics? No, third? Okay, that's some folks in physics right now. So we're doing sound and light, which is all waves. Light, sound, travels in waves. And so if you increase the amplitude of a light wave, you're increasing the intensity. If you increase the amplitude, you're increasing the volume, right? How does period affect light and sound? Well, if you stretch out the period, you're changing the frequency. And the higher the frequency or lower the frequency in sound tells you what kind of notes you get. But you can also have application to this in, like we're going to take a look at tide problems, high tide, low tide. Take a look at one of those today. You can have number tracking. We talked about this before, like tracking the number of hours in a day over the course of the year, things like that. Ferris wheel problems, where you are on the Ferris wheel. We're going to take a look at a spring, loading a spring with some weight on it, and letting the spring go, and checking its oscillation, trying to come up with a function that models that thing. So we have a lot of application for periodic functions in the real world, but they're geared more towards the math and sciences. Not going to have a whole lot of this in the business world. All right? Okay, we all have those down, ABCDs? I'll take that as a yes, thank you. Comparing these graphs. So yesterday we looked at the first three. We looked at parent function, which is the one that's on the graph right now, the purple one. We took a look at what happened when I stretched it vertically, just a refresher. Stretched it vertically. In this case, it got twice as big in the vertical direction. Then we took a look at B value. How does that affect the graph? It affects the graph's period. Remember that whatever the B is a horizontal stretch factor of 1 over B in my, if I'm thinking about a parent function T table, but it also helps me find period. And in this case, if my B was a 2, we saw how my graph's period, normally 2 pi, shrunk by a half to only pi. So that's why we're seeing 2 cycles of this sine curve between 0 and 2 pi now, because I'm only using pi as a period versus 2 pi. Okay, that's from, did it disconnect? Yes. What now happens with C's and D's? What do you guys want to guess? What do you think is going to happen here with this x minus 2? What's my graph going to do? To the right. It's going to go to the right. So it's like taking those points that are currently on that graph and then moving them to the right too. And if I did that, again, we think of quarter points for our sine and cosines, right? So take the start point, take our max point, take our intermediate point. So first quarter, second quarter, third quarter, fourth quarter, and then move them all to the right too. So this point's going to go and now become here. And that point, which is 1 point something, is now going to become a 3 point something. It's going to come over here. And this 3.14 is going to become a 2 point. It's going to go over there. Or 2, sorry, not all the way over there. It's going to be a 5 point something. Right about there. And same thing with the negative on the bottom. That negative one goes to the right too. And if I did that, I get that. So everything just shifted. Phase shift. Moved to the right too. Now, the reason we see this part of this red curve is just because on the purple curve it was down here and we didn't see it. But as we moved to the right too, it brought it into view. So that's why it's looking like that. And then, finally, what's going to happen here? It's going to move what? Left. No, it's not going to move left. It's going to move up. Remember, left and right movement occurs within the parentheses of x. Up and down movement occurs, in this case, as a constant. So this whole graph should just shift up, 2. Everything just moves. And that's when our B's and our C's, our D's and our A's move to our equations and then, well, our graphs. Okay, is that a good visual there? All right, good little visual of how this is all going to fly here as we work through these problems. So now let's go do some of this. We're just adding on. Give the amplitude, give the period, the phase shift, the axis equation for this given equation of 2 sine quantity x plus 3, or what's that called? Pi over 3 plus 3. So again, I'm showing the purple graph, which is a sine curve. There's a parent function sine curve. We're comparing things to that to kind of get an idea of what has happened. And the very first thing I'm going to do, if I'm going to draw graphs from the equation, is I'm going to identify all the parts. A, what is it? 2, very good. That means, what does that mean? found it. So what? What does it do? Vertically stretches the graph by 2. All right. B. What is it? Good. It's 1. Where do we look for the B's? Right after sine or cosine or tangent. So usually they're hanging out or right in there somewhere. There is no number there, so it's a 1. So my B is 1. Now what does that tell me? Good. It tells me that T is 2 pi over B, which is 2 pi over 1. So it tells me that this graph's period is not any different than the normal sine graph's period. All right, good deal there. How about C? What is C? Pi over 3. All right, good. I hear some of you guys talking about left. But C by itself is just this pi over 3 pattern. We could think of it as always, if you wanted to think of it as always x minus c, then we would say, all right, c is actually negative pi. Let's go to the left. But if we're looking at it like this, we're going to say a plus pi over 3 means my phase shift tells me my graph goes left by pi over 3 radians. So I'm going to kick this graph back to the left, pi over 3. That's going to be where I started. And then D, it's just 3 exactly. It's whatever my constant is. And remember what this is this is your horizontal axis. And a horizontal axis is a line. And a line, that's an equation. In this case, y equals 3 would be my horizontal axis. So I had it up there a little while ago. We have a horizontal line going. There's the center of this graph horizontally. There we go. So there it is, center of the graph. So that means that above the graph, 2. Below the graph, 2. Why am I using 2? Because it's the amplitude. So the axis line defines how it's above or below. I'm going to go above 2, which means I'm going to max out at a height or a y value of 3. And I'm going to go below 2, which means I'm going to minimize at a value of 1. So in between those 2 red lines is where my graph is going to reside. Can't go above, can't go below that. Always going to be sitting in between. All right, what I want you to think about for C and D, I want you to think about it like we did for other functions, and that was our start point. And we think of it like a coordinate. And in this case, our start point is C, which is a left pi over 3. And a D, which is a 3. And that's where this graph is going to begin. This is going to be helpful, I think, for you beginning to graph these things. What you're probably going to do is you're going to end up graphing one period of your function. And then depending on what I ask you for, like I can ask you from negative 2 pi to 2 pi. Which means you're going to have to take that pattern and repeat it so that you see between negative 2 pi and 2 pi what this graph is doing. So we'll start with just graphing one period. All right, so here's what we do. We go and we take ourselves to the start point, and that's where I begin this thing. So if I'm looking at negative pi over 3, that's in thinking of degrees, we're at negative 60. We're talking about radians, so let's go ahead and do it in terms of decimal value. So a negative pi over 3 is the same thing as a negative 1.047, I think, if I remember that correctly. And then our D value is a 3. So that's where we're going to start, negative 1.047. my curve? That's a great question. How do you think I'm going to find my other points? What did we do yesterday? Cut it into quarters. We cut our period into quarters, and we know what happens at quarters of sines and cosine functions. At the first quarter of a sine function, where do I hang out? Generically, where do I hang out? The maximum. The first quarter takes me to the maximum of a sine curve. Where does the second quarter take me for a sine curve? Back to the axis. Where does the third quarter take me? To the minimum. And the fourth quarter brings me back to the axis. If I can remember that, this stuff's a piece of cake. Find your period, break it into quarters, and then go where I'm supposed to go. And that's what we're going to do. What about my quarters? All right, well, we did it yesterday. One of the ways we talked yesterday about doing this was through a T-table. And we did this. Oops, 2 pi. All right, we thought about quarters that way. So we're going to do the same thing, except in this graph, we're starting at negative 1.047 or negative pi over 3. So if we're thinking about a table, we're starting here. We want to think about it decimal-wise, we're starting here. So what's the first quarter from negative pi over 3? What do I add to negative pi over 3 to get myself to the next quarter point? Well, it's relative to what? To answer that question, you must need the period. We need to know the period if we're going to talk about quarters. Because I can't find quarters of something unless I know how long the period is. So this period, we said, was 2 pi. All right, so we're going to cut that period into quarters. All right, so we take 2 pi and cut it into quarters. That means we're going pi over 2, and pi, and 3 pi over 2, and then finally back to 2 pi. So we're going to add that to negative pi over 3. We're going to add a pi over 2 every time to my value until I get all the way down to the end. And again, thinking about it, probably maybe thinking about it decimal-wise. Remember that a pi over 2 is a 1.57. So if I did that, if I had negative 1.047, and I added to it a 1.57, I'm going to get a what? 0.53. Is that right? So 0.53 would be where I would end up for my new graph. We're going to add pi over 2 to each of our original parent functions. So this is going to be 0.53. And then our y values for this graph, we said we know it's a maximum of 5 and a minimum of negative or a positive 1. So my maximum occurs when I get to 5. So my first quarter, 0.53, that's right about there. And I get up there to 5. Then I take my next one, and I have, I'm at 0.53, and I'm going to add another quarter to it. So I'm going to add another 1.57. So I'm going to take this value and add 1.57 to it. I'm going to get 2.10. So we go out to 2.1, and there's my next point. And then I'm going to take that point, 2.1. And I'm going to add another 1.57 to it. And I'm going to get 3.67. 3.67. That's where the minimum occurs. And we keep doing this. take that value, we add another quarter, and we get, what, 5.24? 5.24 puts me back on the axis. Now I have my points to connect and draw my graph. Let's see if we did it right. Yeah, we rock. There we are. There's your curve. So using my table values, having a starting point, that is a shift to the left. I keep adding a quarter to that, creating my other points. And then I get my curve. Yes, sir?
Can you get your period you divide by 4?
Say that again?
When you get your period you divide by 4?
Yes. So it's always a good idea for graphing these things to, once you find your period, divide it by 4. That's what I know I need to add each time to get to the next 4. What if my period was 8 pi? What are my quarters? 2 pi. Whatever I start at, go 2 pi away, there's my first quarter. Go another 2 pi away, there's my next one. Another 2 pi, another 2 pi, until I get out to a full period. All right, questions on this? Yes? What did I add to get from one to the next?
Yeah.
So I took my very first starting point, which we found with my phase shift, which is this guy right here. Negative 1.047 pi over 3, negative pi over 3. And because our period was 2 pi, or 6.28, we divided that by 4, and that's where 1.57 came from. So I get a negative 1.047 plus 1.57. Get a new number. Add 1.57. Get a new number. Add 1.57.
4 times.
I'm going to do that 4 times. And those become my quarters.
How did you get starting point again?
The C-band.
Well, how did you get the negative?
It's always opposite of what you see.
Oh, so,
Yes. All right? So there's the comparison between the two. You can see the graph is stretched vertically. It's moved up. It's moved to the left. But the period is still the same. All righty. Let's check out this one. So application. Here's our first application problem. Get the sitting on the dock of the bay, watch the tide roll away. Who sings that song? Well, actually, the covers do sing that song. Who's the original artist? Huh? You guys know who the original artist was? I think his name is Dobie Gray. Anyway, that is deep. That's kind of like that. All right. So what are we going to do on these? We all understand tides, I hope. Tide comes in, tide goes out. Where's the application for this? Where is the application for this? Okay, yes, true. It doesn't have to be gravitational pull. But in terms of application, who might be interested in the tide coming out and the tide going in? Surfers, dude. Yeah, surfers definitely would be interested in this. But who else might be? Fisheries. Why? High tide, there's more fish. I don't know if that's necessarily true, but think about, okay, so the boat goes out in the wee hours of the morning, empty. Catches all of its fish, comes back. What's different with the boat? It's heavier, which means what? It has more what's called draft. You guys know what draft is on a ship? It's how much of the boat is below the water. The heavier the boat, more draft. So if I go out at high tide, empty, and I come back at low tide, full, what could happen? Depending on the port. You could ground, right? You could ground out, and then you're stuck, and then all your catch, your ice machine goes out. Now all your catch goes bad, and you just wasted all that money in that day. Your catch is worth nothing. So there can be some application to this, for sure. So picture, this is how we're going to start these things. Notice we're relative to, it says here, we're relative to midnight. calculate this not with an x-axis, but now with the time axis as x. And y is going to represent the height of the tide relative to the what? What do you think we're going to base this datum line off of? Like, how are they determining that and that? Relative to the depth of the water. Exactly. You're relative to the ground surface underneath the water. I'm 2 above, I'm 14 above. So this is not relative to sea level, but it's relative to the bottom of the ocean, wherever we're at. Well, it would be an ocean, because we're talking about tide, right? All right, so we got a couple things we got to be careful of. We're working from midnight. Midnight is 12 a.m., and then we go 1 a.m., 2 a.m., blah, blah, blah. But also, we're going to express these hours right here. We're going to express the hours using decimals. And here's an example. 9:18 a.m. is the same thing as 9.3 hours from midnight. So how do we get the 0.3? 18 divided by 60. Take your minutes, divide by 60. Now you're at a decimal equivalent for hours. All right, so this is what's happening. Let's draw a little picture. Where do we start? We're starting, suppose the depth of water, assume the first high tide, 3 a.m. So the combination of this 3 a.m. and this 14 give me my starting point for this graph. So we're going to use that. We're going to start at 3:14. Time from midnight, which will be designated as 0, and then 14 above the bottom of the ocean. So we go over here, we take our little graph. We're doing this on graph paper. We're not doing it on line paper because we're going to be accurate about this. And we're going to go over 3 from midnight. We're going to go up 14, and we're going to put our very first point in there. So, get rid of that. There I am, 3:14. That's high tide. All right, and then go back, check it out. The low tide, the very first one after the very first high tide, occurs at 9:18. And we already know that means 9.3 hours after midnight. And it's an AM number, so we're still in the morning hours. So we're going to go this time, and we're going to get to low tide at 9.3, 2.
Is that your end?
Say that again?
Is that your end point then?
Well, that's a good question. Is it my end point? We'll see if we can answer that in just a second. 9.3, 2 puts me right about there. All right, so the question was, is that my end point? Now, when you say end point, are you referring to the end of my period?
Like, is that when we're talking about on the application, is that what like when you said is that what that means then? Or is this not?
So on that application, probably like the ship grounding out. Yeah, this would be a bad time for the ship to come into dock. Yes, this would not be a good time. I thought you meant end point is in like the end of my curve, and that's actually a good question. So maybe we can answer that. What do you guys think? Is that red dot on that graph the representation of a full period of this curve? Why are you shaking your head no? Doesn't it have to go back to where it started? Doesn't it have to go back to high tide? It has to. Because remember, a cycle starts and ends in the same spot. It goes through one pattern. So to go from high to low is how much of my curve? Half of my period. So what I've got so far, graphically speaking, is something that's doing this. What does that curve look like? You just saw half of it like that. It looks like a cosine curve. Cosine curves, remember, start at a maximum value. They don't start at the axis like a sine curve does. They start at the maximum. So this looks like it's a cosine curve. And on the other side of this would be the symmetric image of this. And so if that's true, that from here to this 9.3 value is representing half of a period, then I can very easily calculate a full period. So if 1/2 of t is equal to 9.3 a.m. minus 3 a.m., what in the world is that? That's something. So if we get 6.3 hours, then a full period must be 12.6. 12.6 hours. All right, now that's period. Is that B? No. Period is not B. Can it help me find B?
Yes.
Yes. Good. So we haven't found any A's, B's, C's, or D's right now. We're just kind of drawing our little sketch. All right, so I'm going to go 12.6 hours from 3 a.m., and that puts me at 15.6, which is 3.3 hours. That's 3:36 in the afternoon. This is where this high tide is going to occur. So I go to 15.6, right about here, and I'm back at high tide. So here's the other side of the curve coming up for my cosine curve. Another half period later. Okay, so let's see if we have everything we need now to find my respective pieces. In order to find an A, we need a max and a min. And we have that. We have high tide, we have low tide. So 14 minus 2 divided by 2 means I have an amplitude of 6. In order to find B, we need a period. We have that. B is equal to 2 pi over t. And we have 2 pi over 12.6. So you guys are going to convert that for me. 6.28 over 12.6 is 0.49. Now we need to look at a C. A C is a shift of the beginning point of my normal cosine curve or sine curve. And we have shifted, yes or no? When I say shift, it means relative to the origin. Have we shifted? Yeah, my starting point is to the right. So my C value is this shift of 3 hours to the right. All right, so we know C of 3. And then finally, I need to know my axis. D, also related to maximums and minimums. But this time, oh, wait. We're adding. So I get 14 plus 2 over 2. Or an axis of 8. So there's the center line, horizontal axis of this graph right here. All right, we have everything we need to be able to write the equation of this thing. So if we did this right, and I put A's and B's and C's and D's into my equation for a cosine curve, I would have y equal A cosine B 0.49 in parentheses. Now it's an x usually, but this is t. We're talking about time. Time minus 3 hours. And then an axis of 8. So there's my equation for this scenario. So now your head honcho dude of the port can calculate when is a safe time for these ships that have full loads to come in and unload their catch. Because of this model. They know what each draft of each boat is. and then they're able to figure out, hey, it's a good time to come in now, or nope, not a good time to come in. All right, there we go. What was this? I think that was just our equation. Yeah, there it is. Right there. Same thing we had. There we go. There it is. All right, we good? Yes, ma'am. Oh, that wasn't a question. I was eating a corn nut. Any other questions or any questions on this stuff? Difficulty, 0 to 10. 10 being difficult. Where are we at? 7? 11. Okay, great. That's right, I'm going to crank up my amplifier to 11. You seen the movie Spinal Tap? It's a music thing, you wouldn't know. All right. If there are no questions, then let's try on our own. Or maybe we should do one more example. What do you guys think? Want to do this? No, let's do this one on our own. Partner up. We're going to partner up for this one. And let's see if we can... All right, you guys help me out here. So remember I say, let's start with a little sketch. A little sketch is useful to figure out what's going on. We were told that the spring is suspended above the floor 36 inches. That's just it sitting there. I haven't done anything to it. It's just sitting there. And then it says that I pull the spring down 7 inches, not down to 7 inches. But I pull it from its 36-inch height down 7 inches, which makes it 29 inches. Now, starting the spring at 29 inches above the floor, that's time 0. I let the spring go, I start my watch, and at 0.75 seconds, the spring is at its maximum height. All of that information was given to us in the problem, right? Where I start, and then I pull it down. Height maximum after that amount of time. So there's my little sketch. Over here on the graph, time axis, not x-axis, even though it's labeled as x. This is a time axis, time. And this is my height above the ground. Now the problem did say for part A, make a sketch of the function that models the height of the spring relative to the floor. Meaning we're having to make our datum line, our 0 line, the floor. So if I sketch this thing at 29 inches, where I start it at time 0, and then 0.75 seconds later, it is at 43, which is putting us right there. So I have 0, 29, going to 0.75, 43. So my sketch looks like this. So I've got some great questions about how do we know that this is a sine or a cosine curve. Here is how you know. Sine curves always start at the axis line, and they either go up for positive sign or down negative sign. Cosine curves, they either start at the max or at the min. If they start at the max, it's a positive cosine. If they start at the min, it's a negative cosine. This one is starting at its lowest point, so it must be a negative cosine. From just this sketch, I am able to physically see, here's the center line, and we'll calculate why it's 36 in just a second. But I'm also able to see that from here to here is half my period, which means if I, by symmetry, took that graph and reflected it across 0.75 seconds, I would create 1.5 seconds later, I would get back to where I started from. From where I begin to where I get to there is 1.5 total seconds. So here's the other thing you're going to know. That if I know max and mins, if this happens, you are very quickly able to find that, this, and that. Because period, for a max to min situation, you're always going to be given a situation where you have half of the period, which means you just double it. Now you know your period. And then from that, we can find our B value. So A, D, and T, just from knowing max and mins. C, I'd have to actually physically get a look at where I'm starting. This one actually doesn't have a C value because I'm starting on the vertical axis. It's not shifted right or left in terms of so it's a cosine curve. I could create out of these sine curves, but we're going with cosine. Yes, Alex?
How do you know that it's negative cosine and not sine?
Because let's go back to generics. This is where you guys, this has to be imprinted in your head. When you sleep at night, this should be running through your mind. You should have this dancing in your head, that is a sine curve, positive. And a sine curve negative goes the other way. So they always start on the axis line for sine.
Wouldn't that just be a negative sine curve going up?
No. Sine going down has to be a negative. If you're saying it's a negative sine curve, you're talking about the red line here?
Yeah.
And you're saying, is that just one that's shifted?
Yeah.
No, because a shift would mean that this point just goes up here, and this point goes up here, and this point goes up here, and I still have that.
Yeah.
Well, that's not what this one looks like. It's upside down. It could be shifted left or right, but it's not an up and down shift. And then here's the other thing that should be dancing in your head. The cosine curve. Positively. The cosine curve negatively. So notice where cosines start. Not on the axis. So it's max or mins.
So it could technically be a sine curve shifted 0.5 to the right?
Okay, yep. So you're going to have multiple possibilities in terms of answers. So you just pointed out that if I looked at this thing and said, hey, I want that to be my starting point so that I create a sine curve, now I have a C value of half of 0.75. 0.375 would be my C. What if I said, I don't like negative cosines. I want to start my curve here. Now you have a positive cosine curve that has a shift of 0.75. So I can have multiple answers for the same problem, depending on where I use my starting point. Right? All right, so we go and we find all of these things. Good questions, people. Good questions. A, real quick. Max minus min divided by 2. 43 minus 29 divided by 2, 7. Now look at, if I'm paying attention, this is my amplitude. Because that's how far I pull it down to start with. D. Go find D. D. Max plus min divided by 2. 43 plus 29 gives me 36. If I'm paying attention, there's D. Because that's where the spring starts before I do anything to it. All right, so those were just from max and mins. And then the other thing we said we can find is this period thing. So finding my B. B is 2 pi over the period. Well, we need to find period first. So 1/2 of the period is 0.75 seconds, which means the period is 1.5. So we're going to go 2 pi over 3 halves. 2 pi times 2 over 3, and we have a 4 pi over 3 B value. And then lastly, and then this is going back to the question of where I choose to start. If we choose to start this graph on the y-axis, because that's where time 0 occurred, I don't have a C. So my equation, when I'm said and done with all this stuff, should look like y equal negative, because it's upside down, a cosine 4 pi over 3 t, no plus or minus because I didn't phase shift, plus 36. That should be my equation for this one. Voila! Oh, that's so fun. last problem here, we've got a sunrise times in Denver, Colorado. And we're going a full year from the 31st of December to the 31st of the following year. And we've got these charts broken down as number of days and the time at which the sun popped above the horizon. And we think about a sun tracking throughout the course of the year. Summer, longer days, winter, shorter days. So if we were to model that, it actually would be periodic in its display. So let's do a little sketch and see what we end up with and see if we can come up with the equation for this thing. So our first thing is take a look at day 0. 7.4 is the time, hours we're talking about since midnight probably, or what are we talking? Yeah, after midnight. So at 0, 7.4, we would have our first point. And let's just go by 30s here. So at 30, I would be at 7.2, just slightly lower. And then at 60, 6.6. Then at 90, I'd be at 5.8. And anyway, I can keep plotting these points, but why don't we go look for maximum and minimum values. So maximum occurs there. 7.4 is the largest time we have, and then we go find the smallest value. And it looks like that is occurring here at day 165 at 4.5. So we're going to go out to 165. Right about here, and then go up to 4.5, and that puts us roughly right there. So we can see we've got this looking shape that occurs between this maximum value of 0, 7.4, and then this lowest point of 165, 4.5. And as we've been working with the other problems, we said that once we know maximums and minimums, we can very easily find our axis line, our amplitude. We can use this information to find my period because of the fact that the half period is what is occurring here. Whenever I go from a max to a min, it's always half my period. So just from this information, we go and we find all of our respective parts. So our A, max minus min over 2, we have 7.4 minus 4.5 over 2, and that's going to give us a 2.9 over 2, which is a 1.45. My amplitude. Then, let's see, go ahead and talk about V since we can find it. V is 2 pi over the period, and we said that our half period was represented as 165 days. So that means our full period is 360. Almost a year. Remember, we're just modeling. So that means we have 2 pi over 360, or pi over 180. That's my B value. C value. In this example, because we're assuming our start point to be at the vertical axis, we have not shifted right or left. So we're going to say our C value is equal to 0 there. And then finally our D value. Again, we're talking about this centerline axis. D is our max plus our min divided by 2. So we have 7.4 plus 4.5 divided by 2. That gives us an 11.9 divided by 2, which is a 5.95. So that would be the center line axis. So 5.95, almost 6. Cuts my graph right down the middle vertically. I mean, horizontally, but splitting vertically. All right, and I have all my parts now. So from the A, B, C's, and D's, we're able to write our equation. That y would equal A. Now, what kind of graph is this? Looks to be cosine, starts at a maximum, goes to a minimum. So we have a cosine of, now I'm just going to leave it in terms of this pi, although we could probably convert this to a decimal. Pi over 180 is my b value. And then no shift, so we're going to leave t time of day is just t, and then 5.95 is my d value. And that would be my curve.